Hello, everyone. Good evening, and welcome to one of our special VEEPs. VEEP stands for Virtual Exploration Experiences with the Planetary Sciences, and we are all welcoming you for Earth Day. Tonight, there's a special presentation by Dr. William Stefanov. He is a manager of the Exploration Science Office within the Astromaterials Research and Exploration Science Division at the Johnson Space Center. Dr. Stefanov serves as an International Space Station Program Scientist for Earth observation, supporting continued use of the ISS as a remote sensing platform. Without further ado, I bring to you Dr. William Stefanov.
Thank you very much, Sherelle. Let me pull up my presentation. Thank you very much for joining us this evening. Hope everyone's doing fine in these unusual times in which we're living. Before I get into the presentation itself, I just wanted to put out a really baseline definition. What I'm going to be talking about are instruments which are used for remote sensing. And if you haven't heard that term before, simply put, remote sensing is the science and technique of collecting information about a material or surface or an object without physically interacting with it. And as an example of that, this is what your eyes and brain do all the time. This is how you can look outside of a window and see a car driving by and say, oh, that's a car, or that's a dog, or a cat, or a person. It's because your eyes are collecting information, bringing that information to your brain, and your brain is figuring out what your eyes are looking at. So the human eye-brain system is the first and still, in many ways, one of the best remote sensing instruments ever. But as we've developed and gotten more technologically sophisticated, we realize that as human beings, our eyes are only sensitive to a very small part of the whole electromagnetic spectrum. Our eyes are really only sensitive to red, green, and blue, visible colors. Even within that range, like I said, we do a fantastic job, and our eyes and brains have served us well for millions of years. But we also realize that in other parts of the electromagnetic spectrum, like the ultraviolet, or the near infrared, or the mid-infrared, or thermal infrared, or radar, all of those wavelength regions also contain a lot of very useful information on things like material properties, elemental compositions, health of living creatures. And so we have developed technologies which enable us to access those parts of the spectrum and convert that information into something that our eyes can see. Usually really brightly colored pictures, but there are other ways to do it as well. So for that, I will step forward. Why am I talking about the International Space Station as a remote sensing platform, where there's been numerous other robotic satellites since the early 1970s that have collected publicly available information on the Earth. So why am I talking about the International Space Station? What does that bring to the table? Well, one of the main things is what you're seeing on the screen right now. It's the orbit of the ISS around the planet. And I'll say ISS for International Space Station. It's an inclined equatorial orbit. And what this allows the ISS to do is collect information over various spots on the Earth at different times of day and night. Now, this is different from most of the traditional remote sensing instruments on satellites like Landsat, which you may have heard about. Those are designed to pass over the same spot on the Earth at roughly the same time of day on about a 2-week basis. So that's really good for collecting a very constant, very well-defined data set over a long period of time. It makes it very easy to use for science, to compare from one time of image acquisition to another. But it also locks you in to that specific time window, which for most of these kinds of satellites is designed to be around local solar noon for the best sun illumination on the surface. So what the ISS does, it in essence allows remote sensing instruments to collect a fundamentally different and complementary kind of data set, because there are certain processes that take place on the surface of the planet that you really only see early in the morning or late in the afternoon, or say you're interested in looking at light pollution or things like that. You want to be able to pass over cities and other areas of the planet sort of in the dark of night rather than in the middle of the day. And this is what the ISS enables us to do. So now what I'll do is I'll step forward and just talk about some of the sensors on the ISS. Since I do work for NASA, so I have to have a slide that's full of acronyms. This is a picture of the International Space Station, as it would look like pretty much from the side. And what you're seeing here is a bunch of the different sensors that are present on the exterior of the space station. Let me see, you should be able to see my cursor. So you can see like these areas, these external logistics carrier spots, the Japanese exposed facility for the Japanese experimental module, the Columbus exposed facility, which is from the European Space Agency. These all host various external sensors. There's also another aspect of the ISS that makes it unique among remote sensing platforms, and that is because there are humans on board the International Space Station, astronauts and cosmonauts that have been on the station since 2000 continuously. And they live and work inside the volume of the space station, and they can take images through the station windows of the Earth. And they have done that since 2000. So the advantages here are, because you have human beings on the station, they can look outside the window and quite literally see something going on the planetary surface and decide to pick up a camera and take a picture of it. That is the focus of what? Always work better in rehearsal. Okay, so this is the astronauts' activity. We call it Crew Earth Observations, and their whole system is called the Crew Earth Observations Facility. And there you see astronaut Christina Cook, who has about ready to take a picture out of the ISS cupola, which is this an observational node, or blister, if you want to think of it that way, on the bottom of the space station that allows them to look at Earth and also take panoramic images out of the windows that you see there. Now, these cameras that the crew uses are commercial off-the-shelf camera systems. If you really wanted to, you could go and buy exactly the same kind of equipment that the astronauts currently use in orbit on the ISS. You'd probably have a little bit more difficulty using some of the really long lenses that they have in full Earth gravity, but if you want to reproduce the system, you can. And so the way this works is the team here at Johnson Space Center on a daily basis looks to see what science, educational targets the crew can see, and we develop a target list for them that we send up on a daily basis that points them to when and where they can take the images that we would ask them to take from the space station. Another thing that they do as part of this activity is they collect information for disaster response. And an example of that is shown here from about a year and a half ago, a little over a year ago, for California wildfires. Here you see an astronaut photograph, which is laid on top of a Google Earth image, and it shows the extent of the fire plumes coming from the wildfires. Now, as these are commercial off-the-shelf cameras, one of the things that the team here at JSC has spent a lot of time doing is developing the ability to take that camera image and fully georeference it. And by that, I mean, put geographic information to every picture element in that image so that it lies correctly on top of the Earth's surface. Particularly when you're doing disaster response, this is a critical thing for your data to have, because you need this information to lie correctly on top of street grids, road networks, to show where stream courses are, because that's what helps first responders to actually go to places that they need to get to save people's lives and property. And this is something that we've been doing on the International Space Station since about 2012, collecting data for disaster response. Now, moving forward, we can also take panoramic or very oblique data, as I mentioned earlier. And one of the things that is of great interest to both science and hazard response folks are storms, hurricanes, which we are all too familiar with here. And so we take not only images of the land surface before and after the storm has passed, we can also take imagery of the storm system itself. And this kind of information is very valuable for people studying hurricane storm dynamics, trying to figure out how they can track how storms are intensifying or weakening as they travel across the ocean surface and then interact with the land. So here, what you're looking at here is an image that the crew took of Hurricane Dorian last year, which caused quite a bit of damage in various parts of the world. And at times, the crew, if the ISS is directly over the storm, we have some imagery where you can actually look through the eye of the storm to the land surface underneath, which is really cool to see. Moving forward, now I'm going to continue my whirlwind tour. So we can open up some questions. I'll talk a little bit about just a few of the other sensors that are on the ISS, just to give you a sense of the kind of data that's being collected right now. And the first one here is the SAGE-3 instrument, the Stratospheric Aerosol and Gas Experiment. And this is a mission, a sensor that's focused on looking at ozone in the stratosphere, how ozone is created, how it's destroyed. And as I'm sure most of you know, there's a hole in the ozone layer that actually has been recovering over the years. And SAGE-3 is one sensor that's kind of tracking how that recovery is going. Another sensor on the ISS is called EcoStress. You can see the definition of that acronym right in front of you. This is a mission focused on looking at heat stress in plants. And one of the science goals of this mission is to track how plants are becoming more stressed as global temperatures are rising. And so here you're seeing a map that's showing an evaporative stress index, how much water the plant is trying to take in to regulate its temperature, and how stressed it's being if that water isn't available. And this is for part of Central America. And you can see that quite a few of these plants on the Pacific Ocean side are under a fair amount of evaporative stress. And so over time, as the EcoStress mission continues and collects data, they'll be able to start reaching some conclusions as to how rising temperatures are affecting plant stress globally. Another sensor that's been operational for a little while now on the ISS is the Orbiting Carbon Observatory, OCO3. And here they're looking at the dynamics of carbon dioxide in the atmosphere and how it exchanges with carbon on the ground surface. And as I'm sure you've heard before, one of the major greenhouse gases that helps to warm the atmosphere and the planet is carbon dioxide. And so this is a sensor system that is designed specifically to look at and map how carbon dioxide is varying in the atmosphere across the planetary surface. And again, this is another sensor that has a tie back to seeing how things are changing as temperatures are increasing around the planet. Another class of sensor that we have are what we would call hyperspectral sensors. And these are sensors, in this case, this is the DSIS. This is the DLR Earth Sensing Imaging Spectrometer. It's a German sensor that is actually being run by Teledyne Brown Engineering, a commercial company. So this is data collection for fee. And one of the uses of this kind of sensor is to really get at that sort of material identification that I mentioned when I first started the presentation. And this is what you typically see. This is accessing some of that information that I mentioned earlier. In this case, it's information in the near infrared portion of the spectrum that our eyes can't see, but contains a lot of very interesting diagnostic information on what kind of minerals might be present on the Earth's surface. And when you collect all the information that this sensor obtains and plots it out with wavelength, you get something that's called a spectral signature, which an example you can see on the right side of your screen. And these serve as fingerprints, if you will, for specific minerals. And by taking some of this information and picking three colors that are appropriate for different features, you can produce maps like you see on the left side, where different mineral types show up as different colors. And so you can very easily use this kind of information to enhance geologic mapping. You can look to see if some sort of a hazard has occurred, if a landslide has occurred. You can use this to map where deposits are, if a volcanic eruption has occurred. You can use this kind of information to map where ash, say, has fallen on the land surface. And now, the last one that I'll talk about is a laser system. This is the JEDI, the Global Ecosystem Dynamics Investigation. And what this sensor is doing is it's mapping the 3D structure of the Earth's canopy, the Earth's vegetation canopy. And so what you're seeing here is an animation that shows kind of schematically how the sensor works. It's located on the Japanese exposed facility. And what it does is it fires rapid laser pulses down onto the land surface. And these laser pulses interact with the plant canopy as well as the ground surface underneath. And when you collect this data, it maps the amount of time that it takes for the laser to hit the land surface and then pop back up to the sensor. You can use this information to then map things like the canopy height, the height of the trees, the height of the ground, and the elevation changes in the land surface, and also variations within the canopy itself. So what this mission is doing is it's making a three-dimensional map of the canopy surface of the Earth. And again, they're wanting to see how this may be changing over time as temperatures are changing and plant species are changing in response to that. So that was a very whirlwind tour of some of the things going on in the International Space Station. If you'd like more information on all of the sensor systems that are currently operational on the ISS, you can follow the link here. This is the top of this slide. This takes you to the ESRS site at JSC, the Earth Science and Remote Sensing Unit. And there we maintain a listing of past, current, and future ISS remote sensing systems. So I encourage you to visit that site if you have more questions about what's on the ISS right now. So I'm happy at this point to take any questions that you might have.
All right, thank you, Dr. Stefanov. That was a wonderful presentation. There is a question in our chat box for you. The question reads, is there any known effect of this spectrometry on the environment? Are there any interface with the telecommunications?
Okay, if I'm understanding the question correctly, you're asking is if the sort of the hyperspectral information, does that have any use or uses for the telecommunications industry? I believe. And if that's the question, the answer is yes, it can. From the standpoint of, say, sighting a cell phone tower or things of that nature, the kind of information you can collect with a hyperspectral instrument can tell you something about the soil or rock properties that you might encounter in a specific site. And so that might help you derive geotechnical information on how competent the soil is or how solid the rock is. That would feed directly into what kind of engineering you would have to do to build a structure to support telecom types of equipment.
Dr. Stefanov, just a flip side of that question, though, just getting at what I think might have also been a question in some people's minds. The imagery, the data that you're collecting is all passive. You're not actually sending signals down to the Earth. You're just collecting reflected sunlight, correct?
For many of the sensors on the ISS, that's correct. But for sensors like the JEDI LiDAR system, that is an active sensor system. That is actively using laser pulses to collect information on the Earth's surface. And in the past, there have been other sensor systems on the ISS that have used radar information as an active system, like the RapidScat sensor, which was looking at sea surface variations and using radar information to look at variations in surface roughness and relate that to wind patterns on the sea surface. So the ISS can actually support both kinds of remote sensing. It can support both passive optical, passive thermal, and active radar and LiDAR.
Would the LiDAR have any interference with anything that people do on the ground?
No, typically not. The wavelengths that those lasers operate at are not something that you're going to feel. They typically interact with just the whatever on the land surface. So, I mean, yes, you could interact with your car, but it's not something that you're going to feel.
Cheryl, I think there's more questions. I can't see them. They're going just to you. I'm sorry.
Oh, no, that's okay. Next question is, the image that you have on the screen, what is this?
That's an excellent question. It's a recent image. What you're looking at are the Himalaya, part of the Himalaya range in Nepal. And this was taken in early morning. So you're seeing early morning light just starting to hit the faces of the Himalaya mountain range. And this is one of the kind of images that the astronauts can collect from the International Space Station that is a little bit more difficult to collect with more traditional polar orbiting satellites, because you're seeing, this is what we would call a very oblique image, in that it kind of, you have a sort of a sense of perspective and three-dimensional aspect of the ground surface due to the viewing.
Okay. Next question is, are you able to image or imagine the depth of pollution by country, and to imagine its density? Are you able to imagine the depth of pollution by country and to imagine its density?
At the moment, you can get at some parts, some measures of air pollution, but the sensor that was most applicable for that kind of study, unfortunately, is no longer operational on the ISS. There was a sensor called the Cloud Aerosol Transport System. And one of the things that sensor collected was information on particulates in the atmosphere. And they were specifically measuring how those particulates varied over different parts of the Earth, specifically how they were carried by different wind patterns. But right now, there is no sensor on the ISS that is specifically dedicated to looking at air pollution.
Okay. Is some of the data you can collect used for enhanced weather predictive analytics?
Yeah, some of the data that's been collected for hurricanes has certainly been used to get at things like hurricane intensity. When the rapid scat sensor was operational that I mentioned earlier, the radar sensor, that information on wind speed, surface wind speed, was fed directly into local and regional weather information. So yes, there have been sensors on the ISS that have collected information that can feed into that kind of application.
Okay, this is quite interesting. Next question. If you get so much information on the ISS, could you also get information about those cruises or huge boats that have disappeared?
I think, are you talking about things like things like the Bermuda Triangle or something of that nature?
Well,
or just in general. We have had calls, say when there's been some of the jet airliners that have disappeared and have crashed. As part of our disaster response from the ISS, we have attempted to collect information in areas like, say, looking for debris on the ocean surface. In many cases, that debris is too small for the sensors on the ISS to really be able to solve it. But we do try when we get that kind of request. So we do try to respond to that the amount that we can. But for that kind of application, you're typically needing to use sensors that have much higher spatial resolution than what the ISS has.
Okay, and here's going to be the last question for you, Dr. Stefanov. Thank you so much for your participation. Last question. Are the plans to extend remote sensing on ISS beyond 2024? And what are some of the remote sensing payloads you have in the pipeline? Are there plans to extend remote sensing beyond 2024? And what are some of the remote sensing payloads you have in the pipeline?
Yes, I mean, right now, we will continue to use the ISS as a remote sensing platform for as long as it remains in orbit. And that's very probably going to extend beyond 2024 at this point. We're also actively opening up the ISS to commercial partners, like the DESIS instrument that I talked about earlier, for use as a remote sensing platform. As far as other sensors kind of in the pipeline, there are some NASA sensors coming down the road that will be looking at things like reflectance of light off the Earth's surface, because that's an input that's directly useful for climate modeling. There will also be a sensor that will be looking at dust generation areas on the Earth's surface as to where dust is entering the atmosphere, and being to identify what kind of mineral compositions are actually in that dust coming off. Those are two that come to mind as being in the relatively near future.
All right, thank you so very much for your presentation. Next, we're going to transition to hear from Miss Tina Harte.
Good evening. It's so good to be with you tonight or this evening. I am on the East Coast, so my time's a little different from yours as my shadows are beginning to occur in my room. But the presentation you just heard was about how NASA is working to observe Earth from above. And so I want to share with you a resource that you can use to collect your own data and information about Earth as you're making observations from the surface. Now, do I have, okay, there we go. This is the Globe Observer app. It is a free app that you can download on your device, and there are 4 main components to the device that you can use to observe. You can observe clouds, you can observe trees, you can observe land cover using this particular app that you can download. I went out this morning to collect some cloud observations using the Globe Observer app. And I had a series of screenshots that I was going to share with you that kind of take you through how to look at those. So are you now able to see my?
We can. That looks great. Take it away,
Okay.
Tina.
All right, so the Globe Observer is an app that you can download. You can observe clouds using this one. I went out today to make some observations with my app, and finding it a little difficult to show you that through the camera, I did some screenshots. Starting from the left, we have what it looks like when you initially open up the Globe Observer app. You'll notice that the top tool that you can access to make an observation, globe clouds. And when you go to your next, you select that you want to make a cloud observation. You see the next section where you can do a new cloud observation, which is what I did this morning. And then on the far right, you'll identify the organization from which you're making that particular observation. Then it has a page that will open up where it shows the date, the day and the time, your latitude and longitude from which you're making your observation. And then the second thing that you'll see in the middle is, what does your sky look like? Do you have clouds? Is it a clear sky? Is it obscured? If it's obscured, it may be because there's smoke or dust or fog in your particular area. And then as you identify today, I identified that we had clouds in the sky. And so then it asked me, did we have a few clouds? Were they isolated, scattered, broken, overcast? And you can look and see that as you're using the app, it guides you through with pictures to help you identify what your sky looks like and the clouds that you see. We just introduced 2 different modes to help. If you are an expert at cloud identification, you can go straight forward with the manual cloud identification. But if you are beginning to learn the names of the clouds and about the clouds, you can choose the cloud identification wizard, which will guide you through identifying the different types. I went ahead today with the manual cloud identification for purposes of the presentation. And in the middle, it's going to ask you about contrails. Do you see contrails in the sky? Are they short-lived contrails, or are they persistent and long? They spread across the sky. And then it wants you to give a number of how many contrails you're seeing. And then the next slide would take you to, on the far right, the high-level clouds, what types of clouds that you're seeing. But you'll notice that each step of the way, it's going to show you pictures to help you identify. Now, on the high level, I saw that it was a broken sky, quite a few clouds. Now, this is going to also be asked for not only the high level, but you're looking at mid-level and low level. But for time's sake, I skipped over to the next component that you'll find in the app, and that's going to ask you about the surface condition. Is there snow, water? Is it muddy? dry ground. One of the reasons this is really important for you to identify what's on the surface is just as Dr. Stefanov was talking about what the satellite is observing from above. If you're looking at clouds and you see clouds in the sky, the satellite is looking down from above, and it's going to see and document that it sees white in what it's observing. If you're documenting that you see snow on the ground, that's helping to validate what the satellite is seeing. Because if you say, well, it's a completely clear sky, the satellite's still seeing white. Well, if there's snow on the ground, that could be why. But if there's no snow on the ground and you see a lot of clouds in the sky, then that is indication also to validate what the satellite is seeing from above. And then you have the opportunity to take pictures, and we have scientists that are actually looking at your pictures and identifying those and using those in the research that they're doing as they continue to explore our Earth and how clouds are affecting our energy budget and our climate. Now, another one of the apps that you can use is the tree height, which also complements some of what Dr. Stefanov was talking about tonight. And you can make tree observations below that can be used to help validate what the ISAT-2 mission and the JEDI missions are observing from above. And I can try, Sherelle, do I have time for this 1-minute video, or do we need to cut it off?
Miss Tina.
Tina, while the video is playing, would you mind talking just a little bit about what this cloud information can do for scientists, how it helps them? Reiterate some of that.
Yes, this is a citizen science type project where you can provide observations from the surface of Earth that can be used to validate what the satellite is observing, to help scientists as they're looking at the data from above. They can compare that to the data that you have collected from below.
Awesome. So everyone here can upload this program for free and collect data that can support the science that's being done on climate change and on a number of different topics. Yes?
That is correct.
I do have a question here. What would you say are the key factors that impact Earth's health the most? Anyone want to take a gander at that one? Dr. Stefanov, what do you think? What are some of the key factors that you think impact the Earth's health?
Well, I would say in a broad sense, having a good connection between the atmosphere, ocean, and land systems, I think, is probably critical for the Earth's health. Any point where those systems are interrupted or those patterns are changed, perturbed by any outside force, then that's where you start having things like climate change occurring. Because the Earth will then attempt to reach a new equilibrium with whatever that new perturbation is. I think it's important to maintain the ability of the Earth to exchange material and energy, which is how it does through storms, through plants growing and sequestering carbon, things of that nature.
Dr. Stefanov, you posted an answer, thank you, about not seeing any significant changes to the atmosphere since COVID-19. There have been a few other questions that you or Mrs. Harte could answer. One of them was, let's see, any effect on the thermocline circulation, and how can that affect the Earth?
I would say from the ISS, we probably haven't seen anything on the thermocline. No, nothing that I could speak to as being definitive.
I just received a good one. So Tina, can they download the app even if they don't work for a specific institution? So if they're a teacher or a student?
Yes, the app is for anyone. It's for teachers, for students, for formal, informal audiences. No matter who you are or where you are able to download the app for free.